Hello, this is John Oti. In this demo, we will use the Magsimus Deluxe package to illustrate the creation and calculation of an STT cell concept. A recent NEC and Tohoku University announcement of a spin content addressable memory inspires this design. Here is the rather long web address to the story. And here is the actual web page. An MRAM cell with perpendicular anisotropy is at the heart of the spin cam. Here is an illustration of the cell. The cell state is changed by current-driven domain wall motion. Spin torque transfer brings about this motion. We begin with an empty Magsimus Deluxe session. We have our usual default empty lone group node here. Let's enter a meaningful name for it. Let us edit the system node under the calculation control, and let's specify a dynamic calculation. Let's enter a few other useful iteration control parameters, and let's check this box. This flags the writing of simulation recording data to an external file. This option is very useful if you're going to record a large simulation file. We click OK. Let us add an array component to our design. We click the array icon here, and here in the array specification dialog box, let us enter new sizes for the for a computational cell. And let's enter a new array grid dimension. Under the electromagnetic tab, let's enter a saturation magnetization of 1300. This is a typical value for cobalt alloy film samples. Under the magnetic anisotropy tab, we define a uniaxial anisotropy with a strength of 5000 oersteds. Under the exchange tab, we enter typical A parameters for intra-layer exchange coupling. Under the magnetoresistance tab, we now specify perhaps the most important input for STT calculations by checking this box. We leave checked also this box to use the classical Slawczewski model in the calculation. And under calculation control, we select the Landau-Lifshitz-Gilbert equation to characterize this sample, and we specify an alpha of 0.2. Finally, we specify data output to be generated for the sample as 2D plots during a calculation. The first output will be the electrical current through the sample as a function of time. The second output will be a magnetization curve which simply plots a component of the sample's magnetization vector as a function of time. We click OK to complete the specification of the array component, and we give it each node a meaningful name. Right here in the system view window, this spec here is our new array component. It's barely visible, so we correct for that by clicking the zoom full button, and let's zoom out a couple times, so that's better. We also lock down the design components by clicking this button. That way we don't inadvertently distort the geometry of the design when we use the mouse. Let's take a look at the anisotropy we defined for this sample. We right click it, and in the system view pop-up menu, we specify the show anisotropy attribute, and we click OK, and there it is. These yellow bi arrows represent the uniaxial magnetic anisotropy we defined. Let's get back to the last view, and let's revert back to the former display attributes. Next, let us specify a color coding for the magnetization vectors. Right now it's all in red. Let's apply color coding to it. We bring up the system view pop-up menu, and we use the W component as the guide, the color guide. So there we have it. Let's also edit the color wheel a little bit. So there we have it. Next, we want to define pinning anisotropies for the ends, left and right ends of the sample. We also want to create a meaningful initial magnetic state for our sample. We accomplish these tasks using the external Magomat tool, which can be launched from Magsimus Deluxe. We do so by going to the special menu, selecting Tools, and selecting Magomat here. So Magomat gets launched. It's loading right now, and we are done. Let's first navigate to the view of interest right there. We are going to manually specify the magnetization states of the various regions of the sample. With the magnetic state characteristics selected, we sweep out a region of interest, and then we specify the orientation of magnetization in this region. We accept the specification by clicking the accept button, and there we have it. And we do the same for the rest of the sample. And here again we specify a new direction, click the accept button, there we have it. And now we transfer it all to our Magsimus Deluxe session by clicking the transfer button. Let's minimize Magomat and see what we have. There we have our new initial magnetization state. You can see the magnetization pointing up here and pointing down here, and there is an abrupt domain wall between the two regions. Now let's specify the pinning anisotropies. We select the anisotropy characteristics. We sweep out the first region of interest. We specify the direction for the anisotropy. This will be a pinning anisotropy with a strength of 10,000 OE. We change this attribute here. We click the accept button, and there we have it. We repeat the same for the right end. We actually change the color attribute a little bit here. We change the direction slightly. We click the accept button, and so we have a pinning anisotropy up here and a pinning anisotropy down here. We transfer everything to our Magsimus Deluxe session by clicking the transfer button, and we are done. So let's close Magomat. Here in our session, let's look at all the anisotropies we have defined. And there we have them. We have pin in here, we have pin in there, and here's a background anisotropy we define in our Magsimus Deluxe session. So let's revert back to the prior settings. There we have it. Spin polarized current through the sample is responsible for the STT effects. We now define an electrical circuit for the sample that will produce this current. We edit the group to do so. Under the electrical tab, we can see a depiction of our sample here. We attach a custom current source to it, and we click this button to bring up a dialog box for specifying a signal produced by the current source. We are looking to define a pulse train consisting of a positive and a negative, followed by a negative going triangular pulses. For the first one, to create the first pulse, we click the Add button, and we enter the new data. We preview the signal. So there we have it, positive going triangular pulse. We now add the second leg of the current signal by cloning the first one and then making a few changes to the inputs. Let's preview this one. And as you can see, we just defined a negative going triangular pulse. So we are done with our definition. Positive triangular pulse followed by a negative triangular pulse. So we click OK. Let us define special electrical contacts also for our component. We do so by clicking this button. That brings up the electrical contacts editor. We reset the input. For the input contact, we reset the definition and sweep out a new one. We do the same for the output contacts. And we also check these display attributes. We click OK and click OK here to get out of the group specification dialog box. We now view the electrical circuit we just defined by bringing up the system view pop-up menu and selecting the appropriate attribute. So here is the electrical circuit. Let's move things around for clarity. There. So this is our current source. The current it produces passes through our sample and flows around through this circuit. Let's now complete this design by importing some dummy components from an external design. These components are not magnets. They add nothing to the design. They just provide us with a visual cues as to which parts of our design is pinned. So we click the Import Components button and navigate to the appropriate folder and select the design, and here are the new components. The design is now done. We can now calculate this design by clicking the Run button. Let us do just that. The calculation is now underway. These are plot windows for the outputs we specify for the design. What I have now done is to load in a separate Magsimus Deluxe session a similar design already completely calculated. This design was recorded. Positive current direction is in the U direction from left to right. Electronic flow is opposite to current flow. The electrons are the bearers of the spin momenta that are to be transferred to the magnetization. So spin momentum transfer occurs from the pin regions in opposition to the current direction. Here is a plot of the current that was passed through the sample, and here is the magnetization curve of the sample. Rapid domain wall motion results in sharp magnetization transitions here and here. Let us replay the calculation. You can see how rapid the calculation, the domain wall moved. Let us pause the playback a little while. We see how these markers show the simultaneous variation of current and magnetization. We also see that the reversal is complete even before the current peaks in magnitude. These humps in the magnetization curve is indicative of slight reversals of the pin regions at high currents. Let us complete the playback then. Here we have a domain wall motion, and there we have it. Let us look at the current density distribution in the sample. There we have it. The distribution is symmetrical about the longitudinal axis, and as you might have noticed, the domain wall motion was also symmetrical about this axis. Let us load another related design. This differs from the previous design from the configuration of the electrical contacts. Note also the different shape of the magnetization curve. This one doesn't have humps as in the previous example. Here is the current distribution in the sample. The distribution is asymmetrical. And wall motion should be and so we might expect the same of the domain wall motion to be asymmetrical. Yeah, let's play back the simulation to see that. So we have the forward switching. You see that it was a bit asymmetrical, and here comes the backward switching. Also, it's somewhat asymmetrical, and there we have it. And finally, let us load yet another related design. This one is a little bit more interesting. Notice that the input and output electrical axes are different for this design. Let's look at the current density for this design. There we have it. The current distribution is clearly asymmetrical here. and the wall motion should be a little bit more complicated. As a matter of fact, notice the steps in the forward transition of the magnetization curve. And let us play back this simulation. So here the forward transition is a bit complicated. It doesn't really get to the pinned region. And here comes the reverse transition. It goes right back. And the detail is a little bit more complicated. And with that, we come to the conclusion of this demo. The design files used in this demo are available for download. Thank you.